Hi, my name is Daniel Karavolos, and in this video I'll present my thesis, Orchestrating the Generation of Game Facets via a Model of Gameplay. Computer games are media that weave together many different facets. When a game designer creates a game, they imagine a certain gameplay experience. Typically, they start off with certain mechanics or rules of the game and iteratively develop each of these facets until their synergy results in the desired experience. When the design of games is supported by the automatic creation of content, a similar multidisciplinary approach would be expected. Yet many different approaches to procedural content generation tend to focus on a single facet at a time, assuming that a human game designer will guarantee a suitable context. This work aims to address this problem by generating levels and mechanics simultaneously and evaluating their quality via metrics of the resulting gameplay. A common approach to procedural content generation is to search the design space for desirable content. These algorithms typically use handcrafted functions to compute the quality of the generated content. These evaluation functions can exchange information about the respective game facets, but it is tricky to handcraft a function that judges the complementarity of two types of content. Systems that do create multiple types of content therefore usually rely on expensive game simulations to evaluate their quality and complementarity based on the metrics of the resulting gameplay. However, the complexity of modern games increases the runtime of these simulations to such a degree that at some point this approach becomes infeasible. This thesis proposes a framework for procedural content generation via a model of gameplay that can act as a surrogate for expensive game simulations. By combining the levels and mechanics as input and gameplay outcomes as output, machine learning is used to construct a mapping between three different facets of a game. The learned mapping enables the model to identify the synergies between these facets, which can be used to orchestrate the generation of both levels and rules towards desired gameplay outcomes. In order to demonstrate the feasibility of this concept, we explored the domain of shooter games and developed a generative system that uses a surrogate model for quality evaluation to adapt players' character classes, levels, or both towards designer-specified targets. We have created the following pipeline, which consists of three phases. The first phase is data collection. During this phase, we generate a dataset of maps and classes and collect metrics of gameplay. Levels are created via a combination of constructive generative methods. These methods ensure the existence of multiple paths between the player's spawn positions and spread out the placements of health, damage, and armor pickups. The parameters of the classes, such as HP, movement speed, and weapon damage, are generated randomly. The resulting gameplay of a matchup between two particular classes on a particular map is simulated with artificial agents that are controlled by handcrafted behavior trees. One match lasts for up to 5 minutes or a total of 20 kills. From these matches, we collect the duration of the match and the score ratio between the two players as summary metrics of the resulting gameplay. In total, we collected 200,000 data points this way. The second phase is training a model via supervised learning, using the collected maps and classes as inputs and the gameplay metrics as targets. The best model is a convolutional neural network that receives both the classes and the maps as inputs. It fuses both inputs after they are both converted into a flat factor of nonlinear features. The output layer predicts either the duration, the score ratio of player 1, or both depending on the experiment. The obtained model does a pretty good job at predicting these metrics. This model is based on the assumption that we need both facets for a good gameplay prediction. And indeed, when we train the model on only one of the two facets, the explained variance of the model is reduced. Especially duration prediction benefits from combining both inputs. With the model in place, we move to phase 3. The evolutionary algorithm receives a gameplay target and an initial design from the game designer. The designer can then decide which facets can be adjusted: the map, the classes, or both. Given this information, the system then uses one or more generators to search the design space based on the predictions of the model. The output of the system is either presented to the designer for further adjustments or put directly into the game. Okay, so how do we use this? Consider the following scenario. We have a match between two of the classes from Team Fortress 2, the highly mobile but fragile Scout and the slow but durable Heavy. D1 to D10 indicate the results of playtests on different maps in terms of duration and score balance. The Scout has a slight advantage in terms of score, and the games are medium to long. Now our target gameplay is to have balanced matches of short, medium and long duration, so we run our system and see what happens. When deployed to prolong the match between the Scout and the Heavy, the system has learned to increase the HP of the Scout and reduce the HP of the Heavy, while generally reducing damage, accuracy and range to achieve the desired duration. Note that the current system does not incorporate constraints on playability or diversity of the classes. For example, the general reduction of speed difference between these classes also reduces one of their distinguishing qualities, and at some point a reduced accuracy will become frustrating. When adjusting maps, we see that the system has learned some general rules. For short matches, the pickups are moved to the diagonal between the players' bases for easy access, and the corners of the map are blocked off to reduce exploration. For medium durations, only a few changes are required, and they mostly consist of moving certain pickups to the side of the map. While for long matches, we see more structural changes again. The system closes off certain paths, which makes it harder to get around the map. An interesting benefit of using a convolutional neural network is that we can easily project the activations of the map features back onto the map using an algorithm called Gradient Class Activation Mapping, or GradCam for short. This indicates the most influential areas for the model's predictions. In a design tool, this visualization can be used to show a designer where the design can be changed with maximum effect. As we can see, different targets have different influences, and the influential areas change when evaluating the same map for different classes. We have seen that if you want to predict the gameplay of a piece of content, it is good to take into account multiple facets. Furthermore, gameplay predictions are very cheap surrogates for simulations. If you want simulation-based evaluations with minimal stochasticity, one run would take 12 days instead of 3.5 minutes. Even with a single noisy simulation per evaluation, this process takes 19 hours. Finally, orchestrating facets, instead of adjusting one facet at a time, obtains the same gameplay goals with less changes to the original design. We have taken a first step in demonstrating the feasibility of game facet orchestration via machine learning. While this work has focused on shooter games, the described approach is not tailored specifically to this genre and can be applied to other genres such as real-time strategy games. It would be interesting to see which elements transfer directly to a new genre and which ones need changing. The obtained model can be used to explain changes to a designer. A next step could be to deploy it in a design tool and expand upon the dialogue between the designer and the generator, or even remove the generation part entirely. Regarding this system specifically, directions for future work include incorporating more metrics of gameplay, improving the content evaluation method, and fusing more facets together. All in all, the results of this research promote a more holistic view to procedural generation. While this work is not the only approach to generating multiple facets, we do hope to see more orchestration systems in the future.